All right, we're going to pick up where we left off yesterday, discussing the structure and the function of the heart. We're learning it's kind of complex because it's not only extrinsically regulated, like we've seen so far for other muscle types, but it's also intrinsically regulated. So we made sure to take some time to really understand those cells that make up the nodes, the SA node and the AV node. And we concluded with the action potential in the pacemaker cells. And then we actually contrasted the action potential of those contractile cells. So let's just review that. We learned that the SA node will depolarize spontaneously because it's leaky to calcium. Okay, so in those cells, they'll just spontaneously depolarize, fluxing calcium in and out, and generating action potentials. The flood of polarity diffuses, if you will, from the pacemaker cells through gap junctions into our contractile cells. They'll depolarize with our familiar ion called what? Which ion will our sodium influx will cause our contractile cells to depolarize? Then something unique happened here at our contractile cells, contractile cardiac cells. What was unique? After depolarization, the cell has a plateau phase. What does that mean, and or what causes that plateau phase? It's a brief, it's not just an immediate, it has something to do with repolarization. What does that have to do with? What's happening during that plateau phase? Calcium is slowly coming in, keeping the cell what? Keeping it depolarized. Okay. And so our cardiac contractile cells, they maintain this depolarized state for a period of time before they ever go into repolarization. Does anybody remember what the purpose of that was or is for? Why do we have that plateau phase? Good. It says it prevents tetanic contractions. Very good. What is that? We said those are just so where it freezes up. Okay, so it prevents a contraction from being sustained. It makes sure the skeletal muscle contracts and then relaxes. Very good. And then it'll repolarize like we're familiar with potassium, and then go back to resting membrane potential. Did we plot? Yes, we did plot the myocardial cells on page 3 of your guided notes. And had you guys clearly label that graph as contractile cells or the cells of the heart. Then we left off about there, and just to reiterate what we learned about what creates that plateau phase, the contractile cells also have a refractory period, which we've seen this term before. And what it does is it prevents it, due to that plateau phase, these refractory periods ensure what we were talking about, making sure that once a contraction is started, it will end so that it doesn't sustain a contraction such as tetanic contractions or something called summation, which we've used that word in the nervous system, but the same thing with muscles. Muscle contractions could and add together and maintain, like in a tetanic contraction, which we don't want in the heart. We want the heart to continually pump, right? So contract and relax. And so just like the terms that we use in the nervous system, there's an absolute versus a relative refractory period. And again, the activity of those gated channels during depolarization and maintain depolarization. Basically keep it excited. If it's excited, it's not going to spontaneously get excited again. It's going to go back to that resting period. The next series of events that we're going to talk about are called the cardiac cycle. And to be honest, we've already you have a fundamental appreciation of the cardiac cycle. it's everything that the heart does in the period of a beat. So what do you think? First, what? If we have a beat, we start where? The SA node excites the atria. When we say excite, what are the atria going to do? Contract, or we could use which word? Systole. Then the electrical signal does get past the AV node. Atria will do what? Relax or go into diastole. While they're doing that, the ventricles are getting ready. They're doing what? They're getting ready for systole because electrically they are depolarizing, which allows them to contract physically. And then they've got to do what? Then the ventricles need to relax. Okay. That's going to go, that's all the cardiac cycle does is go through those phases, but adds technical detail with the volume of blood and the pressure that's happening in each of those phases. So that we've not really quantitated much about the volume of the blood through the heart, with the exception of lab that we did Monday or Tuesday. So that's what we're going to add here. And so the cardiac cycle is everything that happens with a single heartbeat, okay, to propel our blood. Reviewing some terms which we learned in lab, including systole and diastole. We learned that if a chamber in systole it's contracting, and the blood in that chamber is what? Is being ejected. Right? So the chamber is emptying of blood if it's in systole. Conversely, we learned that a chamber may also be in diastole. So that means the muscles are relaxing and the chambers are filling up. Okay. And we're going to alternate between those so that the atria, when they're in systole, they better go back into diastole before the ventricles are in full on what? Systole. Okay. Your heart is designed so that it prevents all four chambers being in systole at the same time. What do you think happens if all chambers are in systole at the same time? Heart attack, right? So they're all squishing, there's no blood entering, all the blood's exiting. Just as well, we don't want all four chambers to be in diastole at the same time. Heart attack, something's going on that's not good. And so all those electrical currents, etc., that we've talked about, make sure that the atria, after systole, they go into diastole, while the ventricles are entering systole and then diastole. As I was leading up to, within each chamber, the volume of blood is clearly going to change, as well as the pressure of the blood is going to change within each chamber. You should recall, if you were in a lab yesterday, or if you're going in a lab today, you're actually going to look at an atria versus a ventricle, and all four chambers can contract, but the atria won't need to generate as much pressure because the atria don't need to send the blood near as far when compared to the right and the left ventricles. Okay. So you can start anywhere because it's a cycle. Okay, so I believe your textbook starts with when the ventricles are in diastole, so they're beginning to do what? They just finished up contraction, so they're beginning to relax. They were empty, but now we're adding blood to them. So starting out low volume, and we're going to increase the volume of blood. If we increase the volume, what else is going to be increasing? Pressure is going to begin to increase. Very good. The valves, the atrioventricular valves, and the atrium and the ventricle are open, which indicates why the blood is flowing into the ventricle. So we get midway through diastole of the ventricles, the atria begin to depolarize and get excited. And that's what we learned yesterday, is the P wave can be measured with an EKG. The atria contract, or I could have used the word systole. Okay, so the atria enter into systole. All right. After full relaxation, what do you think the volume of blood is in a ventricle? Low or high? After, at the very end of diastole, the volume of blood should be what? High. Okay, because we just filled it up. Okay. And that volume of blood is called the end diastolic volume. The volume of blood, typically measured in the ventricle, and more specifically the left ventricle, the volume of blood at the end of diastole. So you know that this number is going to be a large number. It should be the largest number, how much ever blood we put in there. So it's described as the maximal volume of blood in the ventricle at the end of diastole. All chambers would have this, but again, because the left ventricle propels the blood out to the systemic circuit, it's usually in reference to the left ventricle. Okay, but all chambers would have blood entering in them. Okay, hopefully. You okay with that term end diastolic volume means? It's the largest number, maximum amount of blood that's in that period of time. After the P wave, we get into the QRS complex, so the atria relax, or go into diastole, while the ventricles begin to enter into, right, as described here, systole. They're depolarizing, they're beginning to contract, and they're beginning to squeeze in the volume of blood. At this point, the pressure gradient between the atria and the ventricles closes that valve, so no more blood's being entered into the ventricle. But the semilunar valve out to the systemic circuit is, what do you think, open or closed? You would think it's open. We've got to generate pressure yet, so it's still closed. So just added blood, and now we're beginning to squeeze on this compartment. Okay, what are we really doing? We're squeezing on something that's closed. We're contracting and adding pressure, right? So we're trying to increase the pressure to get the blood the heck out of the heart. Okay. So the AV valve closed, and semilunar valves are closed, and so our blood volume is constant. And so the blood volume is constant. And at this point, when there's no blood entering or exiting the heart, the chamber, it's called isovolumetric contraction. And so this tells us the chamber is contracting, but the volume of blood is constant. Okay, it's not changing. If you want to add there, the point is to increase what? You said the point is to increase pressure. Because this thing is a pump. When the pressure is enough, the valves, the semilunar valves will open between the left ventricle and out into the aorta, and then our blood will expel out into the systemic circuit. So that's just that high pressure forces those valves open. Remember, the blood's not flowing backwards because the AV valves, right? So it's got to go down this described as unidirectional pathway. The next thing is, at the end of systole, there may be a small volume of blood remaining in the chamber, so the left ventricle doesn't necessarily have to eject at 100%. And so we can have a measurable amount of blood in the ventricle following systole, and it's called the end systolic volume. And again, this volume proportionately should be what? It'll be low. The bulk of the blood went out in the form of what? What is the name for blood that exits the heart per beat? We call that the stroke volume. Okay, so the bulk of it is going to go out of the stroke volume. Okay, but some of it remains in the chamber called the end systolic volume. And at that point, the ventricle has to go back to what? Diastole, right? However, a lot of people say dystole, I say dia to really not confuse you between systole. Okay? So early diastole, the ventricles relax, the pressure drops, and you can loop this back to point 1, right? It's a cycle, so then it continues on again. Just keep the process going, hopefully for a very, very long time. 7 really just is repeating what we learned in point 1. the ventricles relax, the AV valves open, the atria repolarize, the ventricles depolarize, and it just continues on, right? We keep measuring EKGs. Okay. That is kind of a crash course for the cardiac cycle. What questions at this point do you have about this series of events, or these new terms, end diastolic volume versus end systolic volume, or isovolumetric contraction? What do those terms mean? If we have an appreciation for the cardiac cycle, then we can better understand the cardiac output. Figure 13-18 in your textbook reiterates the point which we learned in lab, that the heart does not spend equivalent amounts of time in systole and diastole, as well as the atria and the ventricles alternate those states. And so if we look at the ventricles in the red and the atria in the inner core, you can see the atria relaxed a higher proportion of their time, and a minimal amount of their time is contracting. And the same thing for the ventricles, systole versus diastole. So it's not 50-50, in other words. Okay. Figure 13-19 also reiterates, which we've just learned about the volume and pressure changes within each chamber of the heart. So we're looking at the atria plotted in the pink. Did mess it up this time? In the pink color. And then the ventricle in the green color. But we can really see a profound change in pressure. So if we look at the end the end, this is our pressure, sorry. Is it a volume on here? You can see a huge pressure change in the ventricles, but you notice it's not so dramatic in the atria. It's really minimal, reiterating that structural property of the atria versus the ventricle. But if you look at the pressure of the blood in the ventricles, it's really high, close to 120, which is our textbook, set point for blood pressure, right? So our systolic pressure. You will see it. Do what? This is not a volume. That's what I was thinking it was at first, but this is pressure. So no, it's not a volume. It's just the pressure. It's illustrating that the pressure goes from really high to really low as it's full versus empty. And the more we squeeze on it, the greater the pressure is happening. This as well is a pressure measurement, not a volumetric measurement. At the aorta, I'm pretty sure. Yeah, so the aortic pressure. And this is really what we're measuring when we measure our systemic pressure, like we did in class Monday and Tuesday. Diastolic, systolic, right? It continues, right? Diastolic, systolic. The blood, the stroke volume pulses out there at that really high pressure. And it's due to the ventricle propelling the blood along this journey. The volume that you're asking about is here in figure 13-21. And this is it should be in a ventricle. I don't have it labeled on here properly. But within a ventricle, at the end of ventricular systole, the volume should be really low. And then as the ventricles are finishing up diastole, the volume should be really high. Okay. If we were able to measure the end diastolic and the end systolic volumes by using radio imaging or something like that, we can actually accurately quantitate what? What do you think we could quantitate? What could we calculate very precisely? Do what? Stroke volume, okay? If I know exactly how much blood enters and I know exactly how much blood remains after contraction, the difference would be the volume that's out into the system, which is your stroke volume. We didn't measure it in lab. We don't have the equipment. We're not doctors, but we could guesstimate it, right? And that's what we did. And so in order to determine your stroke volume, you could also determine your cardiac output. Excuse me. Thank you. you may recall, should hopefully recall, from lab that we can quantitate the volume of blood not only per beat, but also per minute. And if we quantitate it per minute, that's called our cardiac output. In order to do that, we need to know our heart rate, and we also need to know the stroke volume, okay? And then to accurately do it, you just find this thing right here under stroke volume is not a negative sign, it's a bullet, okay? So our stroke volume is equivalent to our greatest volume in the ventricle less the least volume in the ventricle. So it's just a subtraction between the two. We can calculate it, or like we did in lab, we can guesstimate it by multiplying what? 2 mils times our pulse pressure. Okay. So if you know your heart rate and you know your stroke volume, you can then calculate your cardiac output, which gives a good guesstimate of the total volume of blood in your body. And so we just, again, not a negative sign, that's a bullet point. Your cardiac output is equivalent to your heart rate or your pulse, okay, times your stroke volume. We measured it in milliliters per minute, but it'd be better converted to liters per minute. Okay, so it's not as a huge, crazy number. Okay. We can visualize liters of blood in a bag instead of milliliters, so it's more tangible for us. Just like any other organ in your body, there's the least amount of work which the thing can do while it's healthy, and there's a maximal amount of work that something can do under extreme conditions, and so the heart too. There's only so much which it can do. And if we were to try to figure out the maximal amount of cardiac output that your heart could do, greatest heart rate and the greatest stroke volume, and greatest cardiac output, you can call that the maximum cardiac output. And then, right, the difference between your maximal cardiac output and your resting cardiac output is called your cardiac reserve. In other words, the range of output that your heart could put out between resting and maximal exercising type of effort. Okay, so there's a range, lower and an upper end of cardiac output that your heart could do. Does that make some sense? You're not a machine, right? Think you're kind of like a machine, but you're not like the machine. You can't just have an infinite amount of cardiac output. So what we want to do now is kind of nitpick this right here to see, well, what can change the heart rate, what can change the stroke volume to thusly influence the cardiac output, because there is a reserve, because there is a range. Before we get into the notes, just a review from where we've been this semester. How do you think I could change the heart rate? Okay, exercising, which is activating what? Epinephrine from my sympathetic nervous system. So if I want to move the heart rate greater than its resting, right, intrinsically controlled system, I can actually activate the sympathetic nervous system, okay, to boost it. If I increase heart rate, my cardiac output will increase. Can this parasympathetic nervous system influence heart rate? Sure it can. You actually know, it can make it relax. You actually should recall the nerve that gives parasympathetic supply to the heart. There is a nerve that I mentioned in lab and I mentioned in class. So the vagus nerve, there you go, good job. The vagus nerve actually does what to your heart? Slows it down. All right, I'm going to put you on the, test you again. Does anybody remember the neurotransmitter from the vagus nerve that causes the heart to slow down? Epinephrine and norepinephrine speed it up. So you've really got one option now. What's our other peripheral neurotransmitter? Acetylcholine. So it's acetylcholine from the parasympathetic nervous system can actually slow down the heart. All right, so we have an idea about heart rate. It can be neurally regulated. It could also be hormonally influenced or humoral. We're okay with those things. The stroke volume has a little bit more impact upon it besides those kind of familiar terms, concepts, besides just the nervous system, besides some other blood factor, whatever the case may be. And so that's what we're going to look at first, is how can we change the stroke volume to ultimately change our cardiac output. So there's three major factors that influence your your stroke volume. And the first is something called preload. And the preload is just a term to describe how much those ventricles stretch when a volume of blood, your end-diastolic volume of blood, enters into the chamber. So obviously, if there's more blood entering, the heart will, what do you think, expand or stretch more. So to make it visually a little bit easier for you, you ever filled a water balloon? If you've ever filled a water balloon, you know that if you add more water, it's going to stretch out. Versus if you don't add very much water. Between the two scenarios, like take two balloons, moderate amount of water, and one you just really stretch it out. Which one's going to let more water out? The one that has more stretch. Okay? Because we have more what? You add more, you let out more. Okay? And so it's the stretching, which is called the preload, which is directly proportionate to the volume of that end-diastolic volume that's entering into it. Okay, so that clearly is going to influence how much is coming out. How much is going in directly influences how much is coming out. Something you may not have really thought of before is the force of contraction of those myocardial cells of the heart, of the atria versus the ventricles. Your heart doesn't beat as strong under every scenario. Okay, so like when you're asleep, your heart clearly is going to have to beat, but it's not going to have to beat as forcefully as, say, you're trying to carry a 200-pound bag up a flight of steps, right? Your heart's going to have to beat really strong in that scenario. The degree and strength which the heart undergoes is considered to be contractility. And so if the heart increases contractility, it's contracting stronger. And if it decreases contractility, it's contracting weaker. And so if the contractility increases, right, how forcefully that volume of blood is squished, the more likely the blood is going to be ejected and be found in the stroke volume. So think about the water balloon that we just filled up. Take two of those that we filled up a lot. If you squeeze one so hard, yeah, all the water exits, and one you just kind of partially squeeze, decrease contractility, maybe some or most, but not all of the water would exit. So same thing, right? The more strong the contraction, the more likely the blood would be propelled out. So that's contractility. Kind of thinking ahead, what do you think could change cardiac muscle contractility? What do you think could cause a cardiac muscle to beat stronger? Not necessarily not the speed, but the force of contraction. What do you think can cause a heart cell? They should always contract, right? But we can activate more cross bridges. What do you think can make the heart beat stronger? You can cheat by turning the page and looking at this kind of, and we'll obviously go through it. But look over the images there on page 6 of your guided notes. What do you think could tell the heart to beat strongly, forcefully? Sympathetic nervous system. When you fight or flight, heart rate should go up, but also what should increase? Because we increased contractility. So epinephrine, norepinephrine causes the contractile cells to beat really strong, more forcefully, than if those hormones were absent. Another factor that influences the volume of blood exiting the heart is called the afterload. And if you remember from our heart anatomy, we learned that the ventricles need to propel blood away from the heart, but it's got to first open those aortic valves. It's going to take a lot of pressure to open those valves, because what's on the other side of the valves? I got blood in the chamber, I got a valve. What's on the other side of the valve? Blood, okay, which is trying to move. There's not like a current, like there's not like cilia or something to say blood, you go here. So if the blood goes on the opposite side of the valve from the previous stroke volume, it's just naturally going to have an opposition. Okay, it's just like a dam and a lake, right? If you got the lake, you got the dam and the river, the water still is going to push back against the dam, right? So if the dam are gone, the water could move one way. So the point I'm trying to say is, although a stroke volume has gone out, it's still giving back pressure. Okay? That the ventricle needs to not only generate enough pressure to get its volume of blood out, but to overcome the water on the other side. So it's got to be more forceful. Okay? That opposing pressure, that back pressure, is called the afterload. Okay? So it's got to contract strong enough to not only just get its blood out, but to keep from other blood coming back in through the open gate, the open valve. So preload, afterload, and contractility. On the bottom of your guided notes, I have an image of two of the three separately, but really one of them's kind of implied in the preload. So let's look at those images. The preload, we said, is due to what? Stretching. More blood, more stretching. If there's more stretching, there's more blood that could be released. Okay. The second image that we have illustrates afterload. It actually illustrates two things. Let me come back to afterload in a moment. In order for more blood to be ejected, we have to increase, what do you think these arrows? Contractility. So if we contract more forcibly, we can generate more pressure to propel blood out. So these little arrows, why don't you just write down there, contractility. So preload stretches. Contractility, as the name implies, contracts more forcefully. And afterload, we learn, is that back pressure. So in this image, the black and white arrows illustrating the blood that's just been previously pushed out, it's there. It doesn't like go away. It's actually giving pressure as well. So the heart has to pump so strong that it not only opens the valves, but make sure the blood goes out and not just flooding back in or something like that. And that extra pressure that has to be generated to force those valves open against that opposing pressure is called what? What's it called? Afterload. Does that help a little bit about describing afterload? So what we're learning is stroke volume has a lot of influences on it, including what's called preload, afterload, and contractility. The question is really, of those three, what is going to have the greatest contribution to increasing your stroke volume, right? So if I go start exercising, which is going to have the greatest influence? So let's look at those things. So we're going to take into consideration repeating, just so we can kind of review, that the heart is not only extrinsically regulated, but it's also intrinsically regulated. So the nervous system, endocrine system, and it's got its own little pacemakers. Hopefully a review statement. We're going to take into consideration the intrinsic and primarily the extrinsic factors that can affect the output of the heart. You have, if this isn't the image from your textbook, you have a similar one, figure 1330 in your textbook. Okay. To illustrate, let me just walk you through the image. This is just looking at our factors used to calculate cardiac output. We've said already the cardiac output is a direct factor of cardiac or heart rate, or your pulse, okay, times your stroke volume. The rate times the volume, okay, equals our cardiac output. What we've been looking at in those three factors that influence stroke volume, okay, so preload, afterload, and contractility, right? And then we also talked about heart rate, how the sympathetic and parasympathetic nervous system can act at the nodes to change the rate. Let's first look at the stroke volume. This is just going to summarize what we've discussed. If we're trying to change the volume of blood ejected by the ventricle, let me point out something. Dashed arrows mean what? Or dashed lines represent versus the straight lines. I'll do what? Inhibiting, right? The dashed lines represent inhibition. The straight lines represent like a positive influence. We've kind of seen that throughout the semester. So if I want to increase stroke volume, I can actually directly increase the end diastolic volume. Add more blood in. That increases, if there's more blood entering, there is more stretching, or what word did we use here? Preload. If there's more preload, that's actually going to directly increase contractility or contraction, which is going to directly influence stroke volume. Okay. So just simply bringing more blood to the heart makes sense, right? Bring more blood to the heart, it's going to send more blood out. Okay? So volume can be increased. But we learned that contraction strength or contractility can be increased not only by preload, it can be directly activated by our sympathetic nervous system. The sympathetic nervous system can directly act on our contractile cells. It can act directly on our contractile cells to increase contractility and stroke volume. So why don't you write here, sympathetic nervous system. Try to write in there, at contractile cells, it increases stroke volume. So our sympathetic nerves terminated our contractile cells to increase contractility, which will influence our stroke volume. Where else can the sympathetic nerves terminate? It influences the heart rate, so where can our sympathetic nerves also terminate or synapse? Neuromuscular nerves. The SA node and even the AV node. So go ahead here. The sympathetic nervous system can also synapse at the nodes. It synapses at the nodes and also at our contractile cells. So my sympathetic nervous system can actually increase not only contractility but also heart rate. And so the influence of sympathetic nervous system, what happens to your heart rate? Or your cardiac output? What happens? Increases significantly. And if you recall from your lab on Monday or Tuesday, if you took your cardiac output at rest, contrasted it to your cardiac output after exercise, it was 2 to 3-fold increase in cardiac output, because we're acting on both factors, not just one factor that influences cardiac output. We contrast that to parasympathetic control. Parasympathetic nervous system can only influence what? Directly can only influence heart rate. Okay. So it must synapse only on which cells? The what? The nodes. I just can't hear. I'm sorry. The parasympathetic nervous system synapses only at the nodes. To do what to heart rate? To slow it. Okay. They want synapse with the contractile cells. So if they're not stimulating, our contractility must probably go what? Which way? Down. If the parasympathetic nervous system's activated, contractility lessens, even though we're not directly inhibiting those muscle cells, we're not exciting them, so the contractility actually goes down. And so in a parasympathetic nervous system, your heart rate goes down directly, and your stroke volume would also decrease. Which makes sense because you're resting. Your cardiac output should be equivalently matched. If we tie this into our Unit 2 material, how the parasympathetic and sympathetic nervous system are playing here, if you will. We have our what's called the cardioexcitatory center. It's a set of interneurons, if you will, in the medulla oblongata that monitor the status of the body. If we need to increase cardiac output, these cells will activate which system? 50-50 not it?
Can you repeat what you said?
Yeah. So I said if our medulla oblongata detects that we need to increase cardiac output, which system would be activated? Sympathetic, right? And so that will activate our sympathetic fibers. If you remember, autonomic nervous system has a preganglion and a postganglion cell. That synapse is at the effector organ. If you look at the image closer, you can see the sympathetic cells in green do terminate not only at the nodes, but also where? Contractile cells. If you need repetition, let's see what the point is. Here it does what to the rate? Right on there you could say sympathetic nervous system at the nodes increases the rate of contraction. Sympathetic nervous system does what to your heart rate? Speeds it, right? You exercise, your heart rate goes up, so it increases it. So here it increases the heart rate, but at the muscles we said we're having a direct influence on what? Contractility. Very good. Conversely, after a period of exercise, which nervous system would take over? Parasympathetic nervous system, and we inhibit that pathway, excitatory pathway, and so we're terminating only on the nodes to bring the heart rate down. So the brain is involved. If we look at what's happening there, two scenarios, sympathetic versus parasympathetic supply. Parasympathetic nervous system, right, acetylcholine inhibits this adenylate second messenger pathway. So you can see the dashed line means inhibition. So we inhibit that pathway. And then conversely, sympathetic nervous system activates the second messenger pathway to increase contractility. It's the opposite effect. Or if we recall from Unit 2 material, the heart is dually innervated, and the effects are opposite of one another. All right, so this is going to be repetitive. Right? So we said sympathetic nervous system, when it's activated, E activity is excited, whatever the case may be. Norepinephrine and epinephrine are released, bless you. The beta-adrenergic receptors, bless you, are activated. Your heart rate goes up. We can also add in there, heart rate goes up and increase what? What we've been saying. Heart rate and stroke volume, because our contractility increases. Very good. Conversely, okay, we said the parasympathetic nervous system, it inhibits that pathway. So acetylcholine is what causes this heart rate goes down, stroke volume goes down. You can call something called vagal tone. Is anybody an EMT in here? Work with medics? ER? Anybody? Nobody? So like somebody. Okay. Not in this lab. Because the vagus nerve releases acetylcholine to lower our heart rate, okay, obviously that could be overstimulated. You could, right, normally we want it to happen to keep us conserving energy. And so your heart rate will slow down. Like when you go to sleep, your heart rate really lessens. It's the parasympathetic nervous system controlling it, okay? What do you think happens if you overstimulate the vagus nerve? Like it's too much. What do you think happens? Fibrillation, okay, so maybe, or even just what? May flutter or may just do it. Just stop. Not even just flutter, but actually completely stop. If this can happen, because the vagus nerve, if you remember, we called it the wanderer. It goes right to the head, the trunk. If, this is where this is interesting unless it happens to you, but you know how when you've got a big bad BM and it ain't working, you bear down, okay? What happens is you increase the pressure in the abdominal cavity, and the pressure can be so much that it presses on the vagus nerve, and what could happen to you in that scenario? You could die. Okay, so it's not funny, but it's very interesting. And I've heard some student stories through the years that they've actually gone on calls. Someone's keeled over on the potty. It's usually like morbidly obese folks or like so much pressure, and then that's it. Do what?
So they say that's how Elvis died.
Is that right?
Yeah.
Okay.
He had chronic constipation and stuff, and that's what ended up killing him. And that's probably all the drugs and other stuff.
That's interesting, I think. A bad way, like horror, you know. I guess that's why there's no photos, right? Let's not document that. This, I want to say, never happens. We have 20 minutes. Yeah. And my little kid, I almost had to call in today. Little dude, like remember the call on Tuesday? Nasty ear infection. So I drugged him up, sent him to school yesterday, and they're like, no. So anyway, he's at home today. So I was almost called in, but I was like, I cannot do this before the third test again. But anyway, we have time, so I'm going to stop the recording here, and then I'm just going to field questions that you might have over your content.